Welcome to The Explainer. I am so incredibly excited you're here today because we are uncovering a hidden yet absolutely massive bottleneck of the modern tech age. We're building these AI systems with just unprecedented capabilities, but we're hitting a massive physical reality check standing right in the way. And that's power. Not just generating the power, mind you, but actually delivering it safely to the servers. So today, we're unpacking a fascinating shift happening right now behind the scenes in data center infrastructure. We're talking about the evolution from 19th century analog iron to these brilliant software-defined power fabrics. Specifically, we are looking at solid-state transformers. Okay, let's dive right into this. 1 megawatt. To really understand the stakes here, we have to grasp the sheer mind-boggling density of what next-generation AI actually demands. For context, a standard data center server rack, the kind that houses your everyday email servers or processes normal web traffic, historically used about 10 kilowatts of power. But AI workloads, they are pushing rack density toward an incredible 1 megawatt per single rack. That is a 100 times increase, squeezed into a single 19 to 20-inch wide piece of physical real estate. To really picture what that 100 times jump looks like in the real world, think about it like this. A traditional 10 kilowatt rack draws roughly the same amount of power as 6 average houses, but a single next-gen AI rack, it draws the equivalent of 600 houses. Seriously, just imagine an entire neighborhood's worth of electricity crammed into a physical space roughly the size of your kitchen refrigerator. Now multiply that and imagine a vast data center filled with hundreds of these racks. Which naturally brings us to the elephant in the room. How on earth can our aging power grid possibly survive this kind of massive demand? Well, the short answer is it's really struggling. When a data center suddenly says it needs hundreds of megawatts, traditional utility grids often can't deliver that kind of capacity for years. And add to that the fact that legacy transformers, those massive grid components that step down transmission voltages, are facing severe global supply chain backlogs right now. The industry literally cannot get the hardware fast enough. And this stark reality is forcing data centers to completely rethink their behind-the-meter power strategies. So the solution that's rapidly emerging is something called the solid-state transformer, or SST. Traditional transformers are fundamentally just huge hunks of iron laminations with heavy copper wound around them. It's a design dating all the way back to the 19th century that relies on basic electromagnetic induction. And SST completely reimagines this entirely. It takes that heavy, hardware-bound iron core and replaces it with special magnetic materials that are tightly integrated with advanced, high-frequency electronic circuitry. When you put the two concepts side by side, the difference is literally night and day. Because the SST uses electronic circuitry to operate at much, much higher frequencies than the standard 50 or 60 hertz of the legacy grid, the physical burden on the magnetic material is drastically reduced. This effectively shrinks the transformer down significantly in physical size. But actually, even more importantly, it transforms the device from just a dumb hardware component into a highly programmable software-defined power fabric. Now, what's really fascinating about this is the unique behavior of AI computers themselves. AI doesn't just sit there sipping a steady, predictable stream of power. When a massive cluster of GPUs enters a learning mode, they operate in total synchronicity, and their power draw wildly pulsates. So a rack pulling a baseline of, say, 1 megawatt can suddenly spike to 2 megawatts, and it might do this 4 or 5 times a single second. And let me tell you, those nanosecond spikes inflict absolute physical violence on legacy grid infrastructure. You simply cannot present this kind of violently pulsating load to standard old-school equipment. It introduces severe harmonics and crazy instability to the utility grid. If you try to power these spikes with backup diesel generators, the rapid oscillation can create a resonance that literally risks tearing the physical steel shafts right off the machines. No joke. And if you try using standard batteries, the high-frequency charge and discharge cycles will just completely fry them prematurely. So how do we actually handle this? Well, the real magic lies in something called multiport power aggregation. If you just use a solid-state transformer to do a basic, simple AC to AC replacement of an old transformer, you're kind of missing the point, and actually, it just adds unnecessary cost and complexity. The real, game-changing advantage unlocks when you use an SST to intelligently aggregate multiple, diverse power sources at the exact same time, acting as a dynamic, high-speed buffer for those violent AI power spikes. It is honestly incredible how much physical equipment this approach just totally eliminates. In a traditional legacy microgrid setup, if you wanted to mix solar, battery, grid, and generator power together, you'd need a whole aisle full of separate boxes. We're talking uninterruptible power supplies, rectifiers, isolation transformers, and completely separate energy management systems trying to talk to each other. A multiport SST physically collapses all of these disparate, space-hogging electronics into one single, highly efficient, unified block. It can seamlessly take in AC from the grid, mix it with DC from your solar panels or fuel cells, and feed the exact required power directly into the servers. Let's look at how this builds into a completely new paradigm of speed, which is absolutely crucial here. Managing those aggressive AI power spikes requires lightning-fast response times. Legacy hardware reacts in seconds. Older digital signal processors or firmware-based controls, they might get you down to a few microseconds, but they quickly hit a computational wall. With a fully software-defined SST, you are suddenly routing and controlling massive amounts of power in the nanosecond range. That's billions of a second. And that is the exact speed required to smooth out the incredibly volatile power demands of a modern AI learning cluster. And all of this speed and software control goes straight to the bottom line because it solves a massive industry headache known as stranded power. In a traditional setup, you have to dedicate a physical hardwired feeder to a cooling chiller. Let's say that chiller accounts for roughly 20% of your total facility power budget. Because it's hardwired, even when the weather is cool and that chiller isn't running at full capacity, that 20% power is essentially trapped. It's stranded. You can't just route it over to compute or you'll trip a main breaker upstream and take the whole system offline. But if you're using a multiport SST that's actively aggregating and dynamically routing power in nanoseconds, you can instantly reallocate that chiller's unused power straight over to your DC server racks. The economics of this are absolutely staggering. In a 100 megawatt data center, dynamically unlocking just 20 megawatts of that stranded power can translate to roughly $250 million, $250,000 million in additional AI compute revenue every single year. You are literally just doing more with the exact same utility connection. Now, solving that introduces our next massive infrastructure hurdle. How do we push more power through the exact same copper wiring? Because even if we have the extra power unlocked, getting it from the data center floor into a rack that is demanding a full megawatt runs into a literal wall of basic physics. The physical copper wiring can only handle so much electrical current before it overheats and melts. So the crucial point here is that today's standard data center delivery is usually around 240 volts AC. When you try to push a full megawatt of power at that lower voltage, the required current is so astronomically high that it just overwhelms standard conductors, creating massive resistive losses. So the industry's inevitable transition, which is heavily driven by these next-gen AI chip architectures, is a huge leap to 800 volts direct current. By jacking up the voltage to 800 VDC, you can push vastly more power down the exact same copper conductor, enabling those ultra-dense compute racks without melting the wiring inside the building. However, moving to 800 volts DC introduces some deeply serious and, frankly, kind of terrifying engineering realities that operators absolutely have to respect. Unlike older 48-volt telecom systems where you could safely touch a busbar without much worry, 800 volts is highly, highly lethal. A short circuit at this voltage can cause severe arc flashes, with temperatures hot enough to instantly spew molten copper. Furthermore, AC power inherently has what's called a zero crossing, meaning the voltage naturally drops to zero 50 or 60 times a second, which makes it way easier for breakers to interrupt a fault. High-voltage DC doesn't do that at all, meaning the protection and insulation systems have to be incredibly robust and highly specialized. To manage all of this safely and rapidly, the entire deployment model itself is changing. You definitely do not build this complex, lethal voltage, highly sensitive electronic setup by hand on a dusty, messy construction site. Instead, these software-defined SSTs are being built in tightly controlled factories, containerized into massive 1.6 to 4.8 MVA blocks. They are pre-integrated directly with the switchgear right onto deployable skids. Then, the whole shebang is shipped on trucks and installed outside the data center in a matter of hours, entirely bypassing the massive construction and commissioning delays that are currently plaguing the legacy industry. Which leaves us with a really critical thought to walk away with today. We are hurtling toward an age of unprecedented artificial intelligence, but we simply can't run the future on the infrastructure of the past. If our software is becoming superhuman, shouldn't the physical power grid running it be just as smart? This shift from static iron and copper to dynamic software-defined power fabrics isn't just a neat little efficiency upgrade, it is the absolute foundational enabler of the AI era. It's an incredibly exciting engineering transition to watch unfold. Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll see you next time.